And girls, welcome back to the drive-through for a little addendum edition, the remix. Let's give it up for learning, class. All right. So this is extra help on 11.4 because it's the most complex chapter we've gotten yet. I have scanned the book, but obviously it's not that good of quality. And so I would encourage you to maybe follow along with your book as we do this video. Okay? This is about tangent vectors and normal vectors. This whole section seems so harmless. And so I don't want to repeat the last video. So I'm not going to just review the notation that we had in the last video, but I want you to know that the hardest thing about this section, or maybe the most intimidating thing about this section, is all the notation. So this should make sense to you. To find a unit tangent vector, you take the derivative of the position and you divide it by the magnitude of the derivative of the position. But what I want you to know is that, and we can look at this example, when you do that, your output is a function. It's a vector-valued function. But here's what's pretty cool about this. No matter what value, this is the unit tangent vector function right here. No matter what value you put in for t, you're going to get a vector whose magnitude is 1. You should pause the video and try it. Put in a 0 for t. You're going to get 1 over 1 times 1, which is 1. Put in anything else you want for t, and you're going to get a vector whose magnitude is 1. So that's the significance of it. The unit tangent vector is a vector at any point on our position curve that is tangent to the line, but it's also a unit long. And you're going to see later how we're going to really use that along with the dot product to find some important things. Okay? So, when you read a math book, I need to be able to get to that later. When you read a math book, one of the hardest things is that they often skip many steps. Okay? So, if you're really getting in depth with the problem and you don't understand how they get from one step to the next, I would encourage you to actually write out the example problem and figure out how they get from here to here, or from here to radical 5, for example. So, we're going to continue on. This is the notation for the principal unit normal vector. Okay? You find it very similarly to how you find the unit tangent vector. And as I stated in the other video, this often gets to be very nasty derivation, nasty derivatives. So you're going to have to practice that and stumble through them so it doesn't take you too long to take the test. You should not have your first stumble on the test. You should stumble a couple times on your homework. Okay, so now let's look at what the unit tangent vector and the unit normal vector show us. Notice that at any point, they are both exactly 1 unit long. But more importantly, they are orthogonal to each other. Okay? So just understand that right now. You should also understand that, and I can tell you that the math on this must be very tough because I consulted my friend Justin, and he couldn't even figure out why it works. That if you take the principal unit normal vector, this one, why it automatically points towards concavity. So, like, if you're really curious, you might want to try to figure that out and explain it to us. How come it definitely points towards concavity when all we're really doing is taking the derivative of the tangent vector? But it's not just the tangent vector, it's the unit tangent vector. Okay. So, right now, all we really understand is that unit normal vectors are a unit tangent vectors are a unit long, and they are tangent to the curve at the point, and principal unit normal vectors are a unit long, and they are perpendicular to the tangent vector. I'll miss you, Matt. All right. So check this out. This is a helix. It's wrapped around a circle whose radius is 2. Radius is 2. And it's going up at a rate of z equals t. So, at every point you can see here, what's being demonstrated is the principal unit normal vector. Okay? So let's take a look at how that involves acceleration, and then we're going to do one little thought experiment, and that'll be the end of the video. Okay? I would really encourage you to read this twice, or maybe 6 times if it takes that long, because that's probably how long I had to read it until I really started to grasp it. And then I'm going to try to explain it to you. But essentially, we are going to use our principal unit normal vector and our tangent vector to determine the components of our acceleration. This is huge, right here. Okay? Those two things determine the plane that contains the acceleration. Here's your proof for it. It's very complex, and I'm sure they skip some steps. But this box here is kind of the crux of the biscuit for this section. It's the only reason the unit tangent vector and the principal unit normal vector are important, okay? So what this is are all the ways that we can find, this stands for tangential acceleration. This stands for normal acceleration. I will explain to you what that means in just a second. But one way we can find it is take the derivative with respect to t of the magnitude of the velocity. So that's the speed. Remember that in previous sections, v was defined as r prime of t. So you could also just put an r prime of t in there. Another way to find it is to dot it with the acceleration. We're going to talk about that. And then this is the third way you can find it. There are 4 ways to find the principal unit normal vector. Although, honestly, there's 4 ways to find the tangent one too, but the tangent one is always easier to find, and this one is harder to find. So I'm just telling you, they could have put a 4th one up there, but you would never use it. Keep in mind, if you're going to use this one, magnitude of the cross product over magnitude of the velocity vector, which is also speed down here, if you're going to use this one, then you have to have a 3-dimensional vector valued function, because you cannot take cross products of 2-dimensional vectors, okay?